So you've all seen the Aurora Borealis, maybe in person if you're lucky, but certainly in a picture. This is a visual and beautiful example of what we call space weather. But did you know that space weather might take out service on submarine cables? I certainly did not have that on my radar, but in this special bonus episode in our submarine cable series, we're going to learn all about it. So welcome to TeleGeography Explains the Internet, the show that explores the business behind all of the ways humans stay connected around the world. I'm your host, Greg Bryant, and my guest today is Shibaji Chakraborty, a research scientist at Embry-Riddle Aeronautical University. Shibaji and I will be discussing the fascinating topic that you may not have considered before, where first he'll explain just exactly what space weather is, the weather conditions in geospace starting around 100 kilometers above Earth. And that includes phenomenon like solar storms that can create powerful electric charges and magnetic fields. Then we'll dive into how this space weather can affect the critical metallic power feed cables that run alongside fiber optic lines to power repeaters on the ocean floor. We'll talk about how water depth and electrical properties of the Earth's crust can actually make certain cable sections particularly vulnerable to these magnetic fluctuations. Shibaji shares historical examples of these storms and discusses a lot of the ongoing research and industry collaboration needed to better understand, model, and mitigate these potential risks to submarine cables. This was an entirely new layer of risk in my knowledge for our global connectivity that I really think you need to hear about. So please first rate the show, subscribe, tell a friend to listen, and of course, find me on LinkedIn with any suggestions or feedback, and enjoy the show. Welcome to the show, Shibaji.
Thank you, Greg. Thanks for having me.
Yeah, absolutely. I think this is going to be a fun little bonus episode tacked on to our submarine cable episode with this really interesting topic that you brought up to us. So thanks for that. Before we jump into it, could you just give us a brief background on yourself and your career and how you came to be a research scientist at Embry-Riddle?
So I'm a research scientist at Embry-Riddle Aeronautical University. Prior joining Embry, I was in Virginia Tech, so where I graduated from as a space weather researcher under Superdon Virginia Tech Superdon Lab. So there I started research on the space weather and electromagnetism. So I worked on the communication systems prior to working on the submarine cable stuff. But my main motivation behind it is like after graduating as a PhD holder, after like from Virginia Tech, I started doing this study with one of the pioneer in the field, Dr. Bottler, David Bottler from Natural Resources Canada. He has this overarching structure of distributed source transmission line modeling systems, which is like modeling power systems or long distance transmission lines across the globe. So they have all these structure for pipelines and long transmission lines like power feed systems, but they didn't have any structures or simplified code base for submarine cables, which is even larger. So I worked on that. I started working on those things.
I mean, this fits in really well, like I said, as a capstone for our little series all about submarine cables. But before we talk about the submarine cable part, I think we got to back up for our audience and just have you explain what is space weather.
Yeah, that's probably the most pivotal point, like based on which everything is. So it is like a geospace. So typically, space starts from, if you go and Google what is space, it starts from approximately 100 kilometers. Sometimes it says 89.9 kilometer, depending upon which book you are looking for. And beyond that, everything is space. So the space weather is nothing but the weather condition over there. Just like the terrestrial weather, or you have another thing called space weather. So the terrestrial weather typically defines by the atmospheric pressure, which is pressure differences in in winds, and pressure differences in temperature differences across different locations.
Right.
So instead of that, so those are all kind of true in space, but also there are additional stuff. For example, electrical charges and stuff like magnetic fields. So all these things commonly constitute as ionosphere and then magnetosphere, where these are much more dominant forces, Lorentz forces. So you started observing again the pressure difference, but in terms of voltages and magnets.
I see.
The differences of voltages and differences of magnetic field, and which can drive them, and they can actually create circuitry within them. It's kind of a distributed, not exactly like lumped sources like resistance and conductance. So they started creating these current across a different location on top of the earth, and they can actually create significant disruption, because these currents are in the, or the voltages are kilovolts and kiloamperes, mega amperes, like this order of magnitude.
So to give us some concrete examples that listeners can work with, something like the Aurora Borealis is an example that
Yes,
we're all familiar with of
yes.
space weather, or we've heard about, solar flare, EMPs that shut
Solar
down electronics,
flares
that kind of thing.
are, yeah, those are solar storms. So the primary source is the sun, and
Mm-hmm.
that actually create these disruption in the geospace systems. Obviously, yeah, you mentioned, I forgot to mention, this Aurora Borealis is one of the primary,
Right.
like a visual representation of what it can happen. You might not see it as a storm, but
Mm-hmm.
it's a fallout of storm, how we perceive it.
Right.
So that's one thing. And then, yeah, the solar storms, the geomagnetic, it's called coronal mass ejection, that is actually coming
Mm-hmm.
from the sun throws out, it's called solar wind. It actually throws out stuff towards the earth, and it can actually interact with this geospace environment, and that
Right.
can create or alter the space weather, which is like a dynamic system. So
I
that is
mean, this is really fascinating. Yeah, and when you think about it from a sort of geotechnology or geo description, like there's a fine line where there's no more atmosphere. It's not like there's a clear, bright line. There's this
yes.
gradient, and things are happening different at different levels of the atmosphere. Now, that is super fascinating to me, but take it down to the very lowest level here, which is underneath the oceans. What impacts could these space weather phenomenon that you're talking about actually have on submarine cables?
Well, in short, it's like it can create induced EMF, just like in
Mm,
very layman terms. So all these different. So if you go back and check the Faraday's law, right? When if you have a change in magnetic field, that can induce a voltage in a
right.
conducting metal. It's a very simple as that. As so you can imagine like huge amount of current flowing through in our upper atmosphere, which is like, let's say, around 100 kilometers, sometimes even few thousand kilometers, depending upon where these currents are located. As I mentioned, it's not clearly, depending upon what type of phenomena we are observing, there can be different. And these current can actually then induce magnetic fields
Hmm.
on top of the surface of the earth and also underneath the ocean. And as
Mm,
you can understand, like the fiber optic cables needs the repeaters, right, at
right.
a specific different locations, for example few hundreds of kilometers, and those repeaters need power feed cables, which are
Right.
typically metallic, and then those currents, those induced magnetic field, and then can induce voltages in those currents. And typically what happens, as I understand, is like these cables, these repeaters are fed by the stable voltage sources on the either side
Right.
of the cable, submarine cables, and then they have a fixed voltage with some maybe wiggle room in their voltage sources. Now, when these currents are induced in the ionosphere and then followed by the magnetic field on the surface of the earth and under the ocean,
Hmm.
they induce some sort of fluctuation on the base background voltage on these conducting metals, and they can create then disruption on the signal that passing through these cables.
Right.
So that's
That
the
is
kind of scenario.
really interesting. All right, so there's a couple of places there, Shibaji, where I want to follow up. One would be, when I first heard of this concept that you brought up, I was thinking that the danger would be largely to the landing stations, but you're saying that the ocean doesn't necessarily shield from these sort of magnetic fluctuations, that this can go into the actual repeaters like on the seafloor. And then my second question is that it sounds like from what you're saying, the danger isn't so much to the fiber optic cables themselves, but to the metal that is used to power them. So the power,
Yes.
the repeaters, the shielding, that sort of thing.
Yeah. So I'll answer the second question first. Yeah. So
Mhm.
you are getting that right, because the fiber optics, they are typically made out of some sort of a descendant of glass, as I
Right.
understand, like some sort of a glass material. So they are not susceptible to these kind of scenarios, at least as I know of. To be
Yeah.
honest,
Yeah.
I'm not completely 100% sure, but
Well, that's why
as
we
I
need to fund this research, right? But
yeah, yeah,
yeah,
as I
yeah.
know of, that is not.
Hmm.
But definitely the metals,
Hmm.
anything
Hmm.
metallic that is going to be impacted. So
Got it.
these things called GIC, geomagnetically induced currents. And
Got it.
now
Okay.
going back to your first question. So
Hmm.
can you repeat your first question? Rephrase it.
Yeah, the first question was about that. So I was initially thinking that probably the primary danger was to the CLS, the cable landing station, that's initiating the signals. But you're saying that there's actually a danger even under sort of kilometers of ocean above it. That the repeaters themselves that are sitting on the ocean floor can also be affected by this magnetic phenomenon.
Well, yeah, to answer your question, it's partially yes and no. To be
Hmm.
honest, it is right. Like, I mean, the water depth, acts like a Faraday cage, but
Right. Okay,
so
that's what I'm getting at.
it
Yeah.
shields some part of it. But the problem is, as you can understand, the cage made out of different holes, right? I mean, let's say if
Hmm.
you are using a Faraday cage of some sort of a metallic boxes, and those metallic mesh are like, let's say, 1 square meter in size, then anything less than 1 square meter of wavelength in terms of electromagnetic wave will
Ah.
pass it
Hmm.
through. So
Hmm.
similar things happen over here as well.
Right.
And as you can understand, it's not like a 0-1 scenario. It's like an attenuation that goes with the water depth. And as you go higher and higher water depth, then the attenuation is higher. But as you come out on the continental shelves, when it starts from one end, let's say from eastern part of USA to western part of Europe, western side of
Hmm.
Europe. So
Hmm.
the cable starts from somewhere Fredericksburg. I'm taking a typical example,
Yeah.
Fredericksburg in
Yeah.
Virginia, right? I mean, that first maybe few hundred kilometers is the water depth is between 100 meter to 500 meters,
Hmm.
and
Hmm.
and the other side is the similar. Somewhere in the Germany is the water depth is around that. And they create, even if those are like few hundred kilometers long cable sections, they might be much more vulnerable together, along with all this
Right.
huge cable, which is like 8,000 kilometer transatlantic,
Hmm.
that can create a significant total voltage fluctuation.
Right. 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 But yeah, I mean, if the last few kilometers of the cable are at least where there needs to be a repeater and the landing station are damaged, then the cable might be down altogether. Right. So yeah. Yeah.
Yeah.
Interesting. So work through with me, Shibaji, like the likelihood that something like this would happen and affect a sort of broad area of submarine cables. So you brought up the transatlantic. That's a good example because there are dozens of cables there. Lots of places around the world have a concentration of cables. So if this, I assume this phenomenon has some sort of limit to the geographic extent. Is my sort of first question there, and then two, help us work out the balance of the likelihood of this versus the sort of level of problems that it could cause.
Well, so I'll take the likelihood first. To be
Hmm.
honest, it depends upon the grade of the geomagnetic storm. So if you go back
Right.
and check the NOAA website, they provide a typical detailed outline of what different types of geomagnetic storm typically can be. It starts with G0, which is like no storm, and then go up to
Hmm.
G5. And this is a logarithmic scale. So if G0 to G1, 2, 3, 4, and 5, it's not linear. So
Right.
G5
Right.
is a huge storm. And to be honest, these are based on the recorded data, which is probably going back to 57 and probably early 1950s, let's say.
So we don't have a very big data set to understand
No, yeah,
this
to be
frequency. Yeah.
honest, we do have some example of what might happen, what might not, and in terms of frequency, which is called the recall rate, let's say. We do understand there are some sort of a recall rate. We have some studies that talks about 1 in 100 year, 1 in 1,000 year kind of typical strength of these events.
Right.
But to be honest, those are typically modeled and some sort of a reconstruction of what people have recorded in a historically. For example, there are
Right.
studies that talks about, okay, the auroral phenomena we observed near the equator, so that's a very big event. That is how people have described this historical event, but to be honest, we don't have a very clear understanding.
Yeah, that's really fascinating. So you get a little multidisciplinary understanding there. You go to history, archaeology, things like that to look for evidence of these having, because they're so infrequent. Then back to the sort of first part of my question is, let's say there's something like very strong on that 0 to 5 scale, a 3 or above or whatever, right? Does it have a limited geographic extent, or is this happening to sort of one whole side of the globe? Take us through that a bit.
So first rule of thumb is, like, as you go up in the latitude, where I don't want to go too deep into the technicalities.
Sure, yeah. Keep it for a general audience for sure.
So
yeah.
If you go up in the latitude, what happens is, like, typically you see these auroral phenomena, the Aurora Borealis and Australis in the South Pole and the North Pole. As you go up in the latitude, the typical understanding is it might have more impact on those higher latitudes of the pole. But having said that, there is this phenomena. So for going back to an example of 2024 May storm, which we typically call it's a Mother's Day storm or Gannon storm. Okay. So it can happen, like you can observe Aurora Borealis near equator, Texas. People have observed, and there are reported event, not only 2024, but going back to, there is a recent storm which is called Halloween storm, 2003 Halloween storm. It happened November, started like 31st of October to maybe in 2 to 4 days it stays. And people observed near like Guam.
Yeah. Oh, wow. Yeah.
Yeah. So they lit up, suddenly the night sky lit up with these different colors, and people have no idea. Then going back to 1989 storm, and people going back to some other older literature, people describe like how early submarine cable 1989 storm that actually showed like around 700 volt peak to peak fluctuation in the transatlantic cable, the similar location we discussed. And then there was a TAT1 cable going back to 1958 storm. They observed 3 kilovolts.
Gotcha.
Which is significant in terms of even people don't have that much of a leg room, I guess, for transatlantic cable. Maybe not, but it is touching that limit of few kilovolts.
Really interesting. Yeah, as a matter of fact, my kids and I went out in Northern Virginia here and saw the 2024 storm, and I mean, you could see it much better with your camera, but you could see it with your naked eye. It was like incredible. Yeah. Okay. So we're still working out kind of the likelihood of this. We also are, it seems, working out the degree of the impact, though it's certainly possible that there would be an extensive impact, particularly maybe for cables that are at a further north or further south latitude. There's not really cables in the very far south, but there's plenty in the north.
So that's one thing, the latitude, which controls how much impact it can create from the extraterrestrial sources. Right. The second thing is which is I mentioned, this is called GIC, geomagnetically induced current, and for current to flow or induction to happen, there is another parameter that plays a very strong role. Not only the water depth, but the different earth crust and layers, and what is their property in terms of electrical properties, in terms of describing how capacitive or resistive they are. So that can actually create another level of impact. And as you can understand, it's not, our Earth is not homogeneous, so it's very different. And even if you go across the same latitude, not all the parts across the different location of the earth has the similar type of this resistive structure, and that can create some sort of a differences across the latitude and latitude to latitude. And finally, I'll put this one, which is slightly scientific. This current structure in the magnetosphere ionosphere I was talking about, they have their own structure. It's not like even if you go through across the globe, they are uniform. We observe these current systems that appear and disappears with time and space, and they have sometimes very sharp and very strong independent location dependence on how intensive they are.
Interesting.
And that can create, let's say, if you go a very short length, sometimes very short cables, let's say there are some cables coming up on the Great Lakes, Canada. It is slightly higher in latitude in terms of where the Tat8 cables are located, probability, but the length of the cables are short. But I'm not exactly sure about the water depth of the Great Lakes.
Right.
But the resistivity, what I understand, the resistivity of the crust and the mental structure of the Earth is relatively higher on those locations, and that can create some sort of a challenges in terms of what we perceive. Even if the cable length is shorter, we can have havocs.
Right.
Fry,
Right. So it's
fry electronics. Yeah.
not just for those big transoceanic sort of spans, but it's very interesting. And again, to sort of put a pin in what you're saying, that there are just differences geographically on the strength of this effect, right? So it's might be difficult to predict and understand exactly where this would have the ability to take out a cable, where it might not really fully affect a cable. Is that what you're saying?
Yes. We have some sort of modeling capabilities, but with the amount of resource we have, we can't able to do it comprehensively for different locations. And
Right.
obviously, it's cable to cable dependent. And another part we haven't touched upon, I might be wrong, I might be right. I'm not exactly sure. We haven't tested the cable property in itself. Whatever we are discussing right now, we are discussing from the standpoint of geophysics and modeling what is the induction
Right.
effect and everything, but we haven't touched upon the cable design. Again, if we wanted to pursue that, money is the funding is
Yeah. Well,
one of the major source of limitation probably, and resources in terms of whether people are interested in doing that or not. Yeah.
yeah. I mean, that really sort of keys me up for my final couple of questions here. First, to your knowledge and where we've developed our understanding of this so far, is there a way that cable operators can currently sort of anticipate or mitigate these risks?
So
Are we
first of
there yet?
So first of all, even before, yeah, I mean, not partially yes and true again. It's not exactly we can't say like we can't have anything to do. It's not like that, but we can't really have complete protection from this. It's like from me, it's like an analogy to earthquake. It might happen. You can redirect some part of it. You can mitigate the risk by saving not exactly human lives here, but something like that. But you can't really move the whole city, something
Right.
like that. So what we can do is we can actually provide for a specific standard of geomagnetic storm like G1 to G5. We can provide some sort of a standard fluctuation expected through a specific cable. Let's say for transatlantic cable at this specific latitude, we can provide some sort of a the wiggle room of the voltage it can expect for a G1 storm or maybe G5 storm, so that if the cable operators or cable designers or design a cable such a way like it is able to withstand 10,000, it is able to operate at 10,000 volts, it can create, let's say, another 2,000 volts wiggle room, so that even the fluctuation goes around that, it did not trip, or the repeaters does not has any type of problem in there. So that kind of things we can do. Second is like even if that can trips, we can provide relatively stable latitudes where the impact can be less. We can provide those kind of understanding, so that you can lay down one or two cables, so that in a kind of a scenario where one of your cable get disrupted, you can actually reroute your traffic through other cables, sort of things like that.
Mm-hmm.
And finally, where we are moving, but to move like that location, like where we can actually forecast, right? I mean, maybe a day ahead or 2 day ahead, so that you can have some sort of a wiggle room to adjust your operations accordingly. What you can do is like for that is like there are two or three different components here. First component is to predict what sun is going to do 2 or 3 days ahead of time. So there are people who are like heliophysicists are doing that. We have made significant progress, but again, 50 years of data in terms of heliosysmology is nothing.
Right. Right.
It's not,
Right.
no, almost yeah, we still facing that data gaps. Then how Earth, like this magnetosphere ionosphere system, is responding, geospace, space weather responding. I'm in partially in that field, so we are trying to
Mm-hmm.
predict those things given a specific scenarios. And finally, the final part is how, even if we understand how these currents are located, how the cables are responding. And on top of all these things, whatever I just said, there is a very big missing link here, is like the magnetic field observations. We need to
Right.
understand, or even like the ionospheric currents, we don't have enough data points to actually find what should happen along this cable. You can imagine all these cables are running through underneath the ocean, and we don't have continuous monitoring what is happening in terms of magnetic field fluctuation on top of the surface of the water, or even
Right.
the underneath the water.
Mm-hmm.
So that's all, these things are kind of limitations right now. Probably once some of them get addressed, as we address some part of it, the prediction capability will enhance.
Yeah, yeah, absolutely, excellent. So it sounds like there's still a lot more research to be done, as you said, kind of across all these different areas in terms of the heliophysics, in terms of the physics of how it actually interacts with the submarine cable, all these kinds of things. How do you think that maybe the industry, the folks who are operating and using submarine cables, might be able to support these efforts?
Well, first of all, they can provide the data. So the first thing is like, because we
Ah,
have a capability called SCUBAS, um, it's submarine cable upset by auroral streams, and the
mhm.
full form of it. So
Got to have an acronym to make it official, right?
yeah,
So yeah, yeah.
so we can actually model it. We started collaborating with the Australia-Japan cable network, and
Mhm.
recently started working out some of the NDAs with Meta and Google. Probably we'll get some data. So first of all, get the data and then test our model. We did pretty good on the historical event. For example, I mentioned 1989 storm, which was one of the
Mhm.
legacy storm, and then going back to 1958 storm, which is again a legacy storm. We call them, these two storms, as super storms for very specific reasons. But whatever happened last 20 years, um, there are a few other storms like these kind of, we wanted to test and validate how good our model is doing.
Right.
To do that, we need validation. And then the final part of it, it's not about the end-to-end voltage. I always mentioned about driving voltage, but also what the voltage is between the repeaters. And
Mm-hmm.
that can, because as I mentioned, right, I mean, there can be a current systems that is very like which is very centralized and located along on top of one cable section, and it can fry only one or two repeaters. It
Right.
might not affect the whole cable. That can happen. So providing the data, first of all, collaboration in terms of partnerships, um, then obviously supporting it from the perspective, if they could provide us some sort of grant, that would
Hmm.
be a very good way to
Money
follow up.
always helps, right?
Always
With
helps.
research, right? So
Yeah.
yeah, it's got to be part of your job as a
Yeah,
researcher.
yeah.
Yeah. Uh,
The project has been funded through NSF, but
mhm.
again, due to various sort of things, we are limited by the funding source. But
Yeah.
yeah, I mean, these two are pretty good. And the final thing is like, again, going back to the model. Again, I mentioned the model. This model is typically driven by from the perspective of geospace, whether and from the perspective of geospace science, Helios science, and the Faraday's law and stuff like those things. But we have a limited understanding of this cable in structure itself, and that might play a significant role in terms of how it affects the overall cable.
Right.
And that is a part where engineers probably are more valuable than a scientist.
Right, and so there you're saying you just need more collaboration with
Yeah.
the industry to get a better insider kind of understanding of exactly
Yeah.
how the cables are operating. So I mean, these seem like this is a good place to make this this sort of call to action. So I appreciate that. So that not just funding, but also data share and just like collaboration on the engineering, so that you
Yeah.
can relate what they actually do on the ground or under the sea, as it were, to your models that you've created based on these various physical models. So that sounds really interesting. All right. So on that note, Shibaji, how can listeners who are interested in this topic keep up with you and your work at Embry-Riddle?
I have a GitHub page, as simple as that.
Of course.
Me. Yeah,
I mean,
if they want to contact me, they can just Google me. The Scubas, they can search for Scubas, but it will pop up too many things in the Google. Scubas with space weather and submarine cable effect, probably with these 3-4 keywords if they search it. Otherwise, Embry-Riddle Caesar website, they can find me. I have the email listed over there. So
yeah, excellent. All right, yeah, and we can put some in the show notes. So
yeah.
Excellent. Well, this has been really fascinating. Yet, very often on this show, I run into things that are new to me. But this was a topic that it was entirely I didn't even know was a thing. So I think that's really fascinating. So thanks for bringing it to our attention.
I didn't even think about it. Maybe 4 years going back when I was conducting the space weather, but in terms of other stuff, I didn't know it existed.
Yeah. And yet certainly all the listeners here know how crucial this infrastructure is to the entire global economy. So it's definitely, we're glad you're thinking about it. Excellent. Well, thank you. Cheers.
Thank you for having me. Yeah, thanks.
Yeah. Thanks for listening. TeleGeography Explains the Internet comes from the experts here at TeleGeography. It's edited and produced by Jane Miller, and it's hosted by me, Greg Bryan. And I also wrote that theme song you're listening to right now. To learn more about our data, jump over to telegeography.com, and we'll see you on the internet.